All right, so we want to talk here about the mean value theorem for integrals. We had a mean value theorem for derivatives that we looked at in the first half of this course. But before we can talk about the mean value theorem for integrals, we have to talk about what we mean by the mean value of a function over some interval. So let's say we had some function here, like we do in this picture, f at x, and we want to find the average value of that function. Well, going back even further, if we had a bunch of numbers and we wanted to find the average of all of the numbers, I don't know, a bunch of y's, okay? Let's say we have n y's. Y's are just numbers, and we wanted to find the average of all of our y values, or y average. What would we do with all of our numbers? Yeah, we would add them all up, y1 plus y2 plus y3 plus dot, 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 all the way up to our last one, yn, and then we would divide by how many numbers we had. Divide this whole thing by n. So if we want to find the average value of a function over a range, we do kind of the same thing. We're going to divide this range up into intervals. How many intervals are we going to have? We're going to have n of them. Okay? We're going to choose a point from each interval, and then we're going to average the y values of all of these individual points. Okay? So how do we do this? Okay? So how wide are our intervals going to be? Well, just like we did when we were dividing these things into rectangles, we can use delta x equals endpoint minus the starting point divided by the number of intervals, our usual sort of width for our little intervals here. And in each one, we are going to have some value of, we're going to choose a point from each interval. So let's say that the point we choose in each interval is going to be an x value. So we're going to have x1, x2, x3, all the way up to x to the n. And for each one, we're going to find the corresponding y value, which is going to be f at x to the 1, f at x to the 2, dot, 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 all the way up to f at x to the n. Okay? And let's average these things. Okay? So our average is going to be obviously f at x1 plus f at x2 plus dot, 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 f at xn, all divided by n. But if we take this expression for our width and we rearrange it, n is actually equal to b minus a over delta x. So let's make that substitution into our expression for the average. So our average is going to be, okay, if I put in sub in n there, I am going to get delta x coming up into the numerator, and I'm going to get b minus a coming down into the denominator. So I'm just going to make that sort of switch. I'm going to have 1 times b minus a, okay, comes down to my denominator, and then I'm going to multiply that by this entire thing here, fx1, okay, plus f at x2 plus dot, 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 plus f at xn. And that whole thing has got to get multiplied by delta x. Okay? So divided by n, my divided by n becomes multiplying by delta x and dividing by b minus a. This part over here should look kind of familiar. I mean, this is like a sum, right? So this is 1 over b minus a times the sum of all of our f at x values times delta x. Let's make that delta a little bit nicer. Not much better, but a little bit better. And we're doing the sum as I goes from 1 to n, not from n to n. Okay. Now, let's make n really large. Okay? Because if we want to make our average really, really good, we're going to increase the number of points that we're averaging together, making all of these little intervals that we're choosing the y values from really, really small. So we're going to let n tend to infinity. So the average value of our function is going to be the limit as n goes to infinity of 1 over b minus a, the sum, I goes from 1 to n, of f at x I delta x. This should look really, really familiar. Okay? If I take out this 1 over b minus a, what do we have? We have this expression from the fundamental theorem of calculus, so we can replace this limit and this sum with the integral from a to b of f at x dx. Okay? So this is our expression for the average value of some function over some interval from a to b. The average is going to be 1 over the difference between a and b times the integral from a to b of our function. Okay? So let's use this thing here to, in an example, let's find the average value of some function, f at x, 4 minus x squared, on the interval negative 2 to 2. And then we're asked the second question here, where does this average value occur? Okay, so what was our formula from the previous page? F average is 1 over b minus a times the integral from a to b f at x over dx. Okay. So we need to apply this thing. What are a and b here? Well, what are a and b here? What's a? What's b? A is negative 2, b is 2. So this whole thing for our average becomes 1 over 2 minus negative 2, subbing those values in, the integral from negative 2 to 2 of 4 minus x squared dx. Yes, I did. So b does equal b. That is always true, so it's not wrong to say that. It's just not particularly useful. We should put in that b equals 2. Thank you. Okay, so let's evaluate this integral here. How would you do this integral? First thing I would probably do is I would evaluate this fraction up front. This is going to be 1 over 4. Okay, so we get 1/4 times this entire integral. If we're looking at this integral, we can probably use the fact that this is a nice symmetric function, and so we can change our integral to be, rather than going from negative 2 to 2, we can do 2 times the integral from 0 to 2 of 4 minus x squared dx. So 1/4, 2 times, let's see, the integral, let's do the antiderivative of 4 minus x squared. Antiderivative of 4 is going to be 4x. Antiderivative of x squared is 1/3 x cubed. And we need to evaluate this from, our limits are 0 to 2. So we'll have, well, we can multiply the 1/4 and the 2 to get 1/2. And then let's evaluate this at the endpoints. We get 8 minus 8/3 minus this whole thing evaluated at 0, which is just going to be 0. And if we, let's see, we need a common denominator here. So 1/2 24/3 minus 8/3 is going to give us 16/3. Is going to give us 16/6 as our final answer. Okay? So what is this? 16/6 is the average value of this function over the range. Okay? 16/6, sorry, 8/3. What is 8/3 as a decimal here? Who's got a calculator? Hey, Yoon's punching away here. So 2.667. So it's 2.6 repeated. Oh, then that means I can take off that dot there. Because it's exact. So my average value would occur right about there somewhere. Okay, that's just above 2.5. Okay. Now, so now that we have our average value, where does the function take on this average value? Well, it takes on that value at 2 places. Here and here. If we label these 2 points C and C, sorry, because they're different points, we should label them C1 and C2. We can see from the graph that f at C1 is equal to 2.6 repeated. F at C2 also equals 2.6. So there are 2 points for this function in this domain from a to b, or on this interval a to b, where the value of the function at those points is equal to the average value of the function, or the mean value of the function over the entire interval. And this is basically what the mean value theorem for integrals says. And here it is. If f at x is continuous on a closed interval ab, then there exists a number x in this interval ab such that the value of the function at that number is equal to the average value of f on that interval. Okay? Or, f of c is equal to 1 over b minus a times the integral from a to b of f at x dx, because that was just our definition for what the average value of a function was. If I take this and I rearrange it slightly, I'm going to take this b minus a, and I'm going to cross multiply. We can write this as the integral from a to b f at x dx is equal to b minus a times f at c. We've seen this expression earlier today. We got that by doing the integral of a constant function. Okay? Okay. So how can we interpret the mean value theorem here graphically? When we did this, we said, okay, what this represented was, this is the area under a constant function, and we could say that that was kind of like a rectangle, right, of height, f at c, width, b minus a. Okay, and that's how we got that area there. Okay. So let's just think about what this mean value theorem tells us graphically. The left side over here is telling us that what we want is the area under the curve from A to B. So if this is our function f at x, we want to find the area under here. Okay. Mean values theorem says that someplace on this interval, there's going to be some value c where the function takes on that mean value. So if c is right, and I should slide c over a little bit here, I'm going to put c right here. Okay, there's some point on there where this thing takes on the value f at c. Okay. Over here, we're talking about sort of the area underneath a constant value. So we're thinking of f at a, f at c, okay, has some value, and we're talking about what you get when you do b minus a times f at c. Well, you get kind of the area underneath this rectangle. Okay? So how does this red area and this blue area relate to one another? This tells us they're exactly the same. Okay? In other words, you can take this little chunk here in green, rearrange it, and it will fill this little space underneath here. Okay? So the area above where the function takes on its mean value and the area below where the function takes on its mean value are going to be exactly the same. So the area above the mean value, area below mean value are the same. They cancel out, and you get that area over there. Okay? So if we wanted to find this number c in the example that we were doing previously, well, what did we know? We knew that f at c, okay, where c is some number, we don't know what that number is, but we know that at that x value of c, our function takes on the average value. We knew what the average value was. It was 8/3. So if we set our function equal to 8/3, and we solve for x, how can we solve for x here? We can do what? X squared over here. Over here we can do 12/3 minus 8/3. 4/3 is x squared. So x is going to equal, if we take the square root, it's going to equal plus or minus 2 over root 3. So these two numbers, plus or minus 2 over root 3, are going to be our values of c, where our function takes on that mean value. Okay? And if we go back to this graph here, yeah, we had c1 and we had c2, and I've drawn them approximately equal to plus and minus 2 over root 3. Okay? So that is the mean value theorem for integrals.